Hi guys, welcome back to the CS Classroom. Today we're going to go over the content for the HL portion of option D. Now, before we get started, a few things that you should know are that the HL portion requires a really strong grounding in topic 5 from the HL curriculum, just because basically what you're doing now is you're taking all of those data structures and you're actually writing them out and using them in Java. So you're going from just having a largely theoretical understanding or just an understanding in terms of pseudocode, and then actually writing Java code with those data structures and methods that we went over in topic 5. Now, you're going to have primarily questions involving these data structures, but also some theoretical questions that are basically like comparing the performance of different data structures and their acceptability or their success in being used in different situations. Now, these are the 5 data structures, and I guess recursion is more of a method of programming that we're going to go over. Linked lists, array lists, 2D arrays, stacks, recursion, and binary search trees. These kind of match up. Well, this one, linked list does match up to something we went over in topic 5. Array lists are a little bit different, but we'll go over in depth what all of these are, as well as their advantages and disadvantages, by completing a basic set of programming tasks for each of them. This is going to be a similar format to the topic 4 and a lot of the topic 4 pseudocode videos. So that being said, let's go ahead and let's get started. Now, we're going to go over some IB specific Java advice. So when you're writing, obviously in option D, you're going to have to read Java code and then write Java code. And you're not going to be on a computer, so it's going to be by hand. Now, the syntax doesn't need to be perfect, but it should be close. So if you decide you want to write your responses in Python instead, that's just really not going to work. Now, one thing I did find online is sort of an obscure document called the JETS booklet, and it's the IB Java Examination Tools subset. And this actually has a lot of the rules for writing Java code for the IB exam. I'm not sure whether you guys have seen this before, but I actually found it really, really difficult to find. So I'm gonna link this below so you guys can take a look at it and hopefully gain some knowledge and understanding of how to write Java code for the IB before you take the exam. As far as I know, it's not available on the exam either. Furthermore, I will be releasing an option D study guide with some really useful code snippets, both just in terms of general Java syntax and in terms of code specific to the IB exam. So what's really important is that you familiarize yourself with how to work with all these different data structures in Java, because linked lists, array lists, and stacks are all going to correspond to specific Java libraries. So you need to understand how those libraries work, even though some of the methods are given on the exam, but not always. So the first data structure that we're going to look at is going to be linked lists. Now, linked lists are included as part of the Java programming language. So we're going to be using a library that is a part of Java. And as a result, it's going to function a little bit differently than the linked list you've gone over in topic 5. And we'll go over what the nuances are. It is also important to know that linked lists are arguably the most frequently appearing data structure. So, I mean, like I said, when I make these videos, I look at past exams from the past 8 years, so since 2014. And I did find that linked lists appeared more than any other data structure. So I think in that respect, it's pretty key to have a good understanding of how to work with linked lists. Now, some of the characteristics of linked lists are that they are doubly linked lists. So if you remember from topic 5, we went over singly linked lists, circularly linked lists, and doubly linked lists. These are doubly linked lists. Each piece of data is stored in a node with pointers to the next node. And these are located non-contiguously in memory. That means these nodes are kind of spread out throughout the RAM, and we only go from one node to the other through the use of pointers, which point to the address of the next node in that linked list. These are particularly ideal for frequent insertions and deletions of elements, or when the size of the list is unknown. So think collections. And part of the reason why linked lists are ideal for this is because in an array, for example, if you want to insert an element, you need to move all the elements around it in order to make space for that one. Here, it's just a question of just basically changing pointers to point to a new node, or taking pointers away from an existing node to delete it. Now, these are some of the methods we're going to be working with. I'll come back to this later. So what I want to do now is, before we move on with the other theoretical information involving linked lists, I want to just go ahead and write some code involving linked lists. We're going to be creating and initializing a linked list, reading an array of objects into linked lists, which is kind of the most common way in which you'll see linked lists. We're going to find and remove a specific object from a linked list, and then we're also going to merge two linked lists into one linked list. And along the way, we'll run into a concept called iterators that may or may not be a part of the code that you write. So let's go ahead and let's move over to Visual Studio to get started. So right here, the main object we're going to be working with in all of our examples is going to be a student object. It's going to have a name, age, major, and grade attribute, and all the accessors and mutators to go along with it. So pretty much every example, like not just with linked lists, but just in general, we're going to be using the student class and student objects. And we're going to be executing our code as usual in a main driver class. Now, if you look at this class right here, we have already created two student objects, name John Doe, I think it was age, yeah, an age of 20, subject or major computer science, and a grade of 85. So what I want to do is I want to start putting these objects into a linked list, and to do that, I want to create a linked list. Now we're going to create a linked list by just typing in, well, first actually we need to import a linked list because it is in fact a Java library. So we're going to do import java.util.linkedList. Now you're not going to have to do this in the exam, but you may see this, and it's worth knowing that it's a library and doesn't just exist organically. So to create a linked list, we're going to do linked list, and we need to actually specify the type of object that's going to be held in our linked list. So we're going to type in student right there because we're going to be holding only student objects in our linked list. So we'll have linked list, just the name of the data structure with the type of object that's going to be held, and then the name of the linked list itself. And we're just going to call that student list. We'll say student list equals new linked list. And then in the second portion, we're not really specifying a data type, but that's how we create a linked list. And in some of the IB examples, you may see it without the data type, but if you write your answer with the data type, that's still perfectly acceptable. Again, look, if we look back at the JETS document that I showed you earlier, if you write like syntactically correct Java code, even if it doesn't look exactly the way it is in the exam, it's fine. So we've got these two, and now what we want to do is we want to use functions to add these objects to this linked list that we just created. So what we're going to do is we're going to say student list, which is the name of our linked list, dot add. And notice we've got a few different methods. We can add first, which will add it to the head of our linked list. We have add last, which will add it to the tail of our linked list, which that doesn't really matter right now because there's nothing in our linked list, but these are other methods that can be used as well. For now, we're just going to use add, and we're going to say we're going to add the James object. And then we're going to do student list dot add, followed by the Jane object. And that's basically how we add elements to our linked list. If we wanted to remove elements, the other thing we could do is we could do student list dot remove, and then we could put in just the object that we want to remove, which is this James object. Or we can also do student list dot remove by index. So in this linked list, unlike linked lists, I think in topic 5, we can actually refer to all of our elements by indices as well. So like if this is the first one, that's going to be an index of 0. If this is the second one, that's going to be an index of 1, and so forth. So if we were to, instead of doing this one right here, we could also do remove just 0, and that would accomplish the exact same thing. Additionally, one other thing we could do, or one other option, is going to be student list. Well, I'm just going to write that code right there. Student list dot remove last, and that would just remove whatever's at the tail of the linked list. Notice, I'm pretty sure we only used the head and tail. Well, we did use those for linked lists in topic 5. Anyways, this would just remove the Jane object from our linked list. That being said, I'm just going to go ahead and copy some code because I want to populate this linked list with just more objects that we can work with, and I don't want to bore you with that process. So right here, I'm just going to copy some pre-written code right here just to add 3 more objects. The only difference really being that right here we are just actually creating the objects inside the parentheses, or like inside the function call right here. So rather than just doing it separately, we're just doing it right in here. And this is creating the student object and then adding that to the student list. So now that we've done that, let's go on to writing some methods that allow us to work with and manipulate linked lists at a deeper level. Now, right here, we want to read an array of objects into a linked list, find and remove a specific object from a linked list, and merge 2 linked lists into 1 linked list. And I think that the precursor, like a pretty natural precursor to that, is to just write a method that allows us to iterate through our linked list and then print out all of the objects in there, like the information about all the objects. So the way we're going to do that is, this is not really important for the IB exam, but we're going to be working in the main class and we're going to write a bunch of static methods. So I'm just going to say public static void, and then display student info, and that is going to have a parameter of, we're going to put a linked list in. So we're going to say linked list student, student list. And this could be called anything. I'm just calling it student list for brevity. But basically, we're going to write a method that takes a linked list as a parameter. Now, what's important to know is that on the IB exam, you're actually, you're not going to have to write these method definitions, but you're going to be writing the code that would go inside this method or a method in order to complete a particular task. Moreover, all of these basic tasks are based on actual exam questions. So rest assured, even if this looks different, you're still learning how to write all the code that you need to be able to write to succeed on the HL portion of the exam. So to do this, we're going to work with an index. We're going to say int index equals 0. Because remember, we can access different elements in our linked list using index. And we're just going to have a while loop. We're going to say while student list, or while index is less than student list dot size, where size is going to kind of function like length does for arrays. So we're going to say while the index is less than student list dot size, and we're going to get every individual element. So we're going to say student current student equals student list dot get index. So basically what we're doing is, well, we're getting, well, actually, let me just add this part right here. Let's do index plus plus. So basically what we're doing is we have an index, and then we're using that index to go to each element in our linked list, and then access that. Each time we access that element, we're going to increment index so that we can continue on in the linked list, much like how we would do with an array. And each time we do that, we're just going to do system.out.println. And I want to print out current student or cur student dot get name plus, we'll put this in quotes, plus current student dot get grade. So basically what we're doing is we're getting the name and grade for each student object, and we're just printing that out. And that's a void method, so that's not really going to return anything. We're just going to print a message out to the terminal. And let's go ahead and let's execute that. So right here in our main method, which is like our driver method, where we execute all these methods, we're just going to execute this static method. And we're just going to say display student info. And then student list, this student list right here is going to be our parameter. Again, this student list parameter just exists inside right here. It has no connection to this one up here, besides the fact that it's the same name. Just to make it clear, we could just call it stud list, or stud list, I guess. And we would have stud list right there, and stud list right there, and everything would work the same. So let's go ahead and execute this. All right, it says the method get is undefined for the type student. Actually, let's go right over here. Okay, so to get name, oh, we just had get right here, so that's an error. Let's execute that again. So we just have get grade. Okay, and if you look right down here, you can see the names of all the student objects, or the names associated with all the student objects, and all of their grades right down here. So that was just really simply iterating through a linked list and just printing out information for each object in each node of the linked list. Now, the next thing I want to do is I want to, some of these questions are going to involve transferring information from arrays to linked lists and vice versa. So the next function we want to write, it's going to be called, well, we're going to write public static, and this is going to return an array of students. Actually, this is going to return a linked list. So let's say linked list student. So a linked list that holds student objects. We're going to call it array to linked list, because what we're going to do is we're going to take a parameter of a parameter which is an array of students called student array, and we're going to return a linked list that contains all the elements in this array. To kind of do that, just to work with that, what we're going to do right here, I'm just going to remove this real quick. We're just going to create and initialize a new student array. So we'll say student stud array equals, and we initialize this using curly braces. And we're going to put the James object and the Jane object in that array. Okay, so we got that right there. And let's go ahead and write this method. So we have a student array as our parameter. And what we want to do is we want to return a linked list that contains all of those elements. So what I want to do right here is I'm basically just going to say, I'm going to create a new linked list. So I'll say linked list student equals, well, we'll call it stud list equals new linked list. And next we want to iterate through our student array using a for loop. So we're going to say for int I equals 0. I is less than student array dot length. And I++ right there, typical for loop construction. We're going to say student list dot add last. We could actually just use add, but add last adds is going to add each element from the student array to the tail, which is maybe just more descriptive in terms of thinking about how a linked list works. Anyway, so actually we're going to call it stud list because that's what our method is, that add last. And we're going to put student array I in there. All right. So now that we've done that, okay, what we want to do is, that's actually pretty much it in terms of adding. I mean, basically what we're doing is we're going to every single element in the student array, and then we're just adding it to this empty stud list right here. And now that we've done that, we basically just want to return stud list. So what we're going to do is we're going to go ahead and we're going to just test this out. So we're going to do, we'll say student linked list new stud list. I'm going to create a linked list called new stud list, and to populate, or to basically get that linked list, to populate that linked list, we're going to do array to linked list, and then stud array is going to be our parameter. And what does this give us? Oh, I kind of messed it up. It's got to be linked list and student. Okay, so what I want to do as well is I'm going to display student info for a new stud list so we can make sure that it actually worked and we can kind of confirm that it did what we wanted it to do. So let's go ahead and let's execute. Okay, so right here we can see we have John Doe and Jane Smith both in our new stud list. So that means that we successfully accomplished that task. Okay, so now that we've done arrays to linked lists, we're going to do linked lists to arrays. So we're going to do public static, and what we're going to do is we want to return an array. So we're going to have an array of students. The name of our function is going to be linked list to array, and we're going to do linked list student followed by student list. And so we're going to take a parameter. We're going to take a linked list of students as a parameter, and we're going to return an array of students. So the first thing I want to do is I want to create an empty student array with the same size as the linked list. And we need to do that because remember, arrays are a static data structure. So the appropriate number of elements need to be allocated before we can add elements to it. So we're going to do student, we're just going to call it student array equals new student, and that's going to have a size. So we're going to have student list.size for the number of elements, because we're basically just taking everything the linked list and transferring it to this array anyways. So our array should have as many elements as does the linked list have nodes. So what we're going to do is we're going to say int index equals 0. And we are going to say while index is less than student list.size. Go ahead and do student array index equals student list dot get index. So we haven't gone over this necessarily before, but we can access specific nodes in our linked list by their index. We kind of talked about that in terms of add up here, but that's basically how it works. So at any given element, we can, or for any given node, if we know what the index of that is in the linked list, which work the exact same way as indices in arrays, we can get that, and then we can put it at that position in the student array. So now that we've done that, we're basically going through every element in the student list, and then we are putting that into our student array. What we're going to do is we're going to go ahead and return that student array. And just to make sure, well, okay, let's go ahead and let's execute this right here. So we're taking a parameter of a student list. So we'll just work with, let's get rid of this right here. So we're going to say, and we're just going to get rid of this. We're going to say students.array, because remember, we are returning an array right here, equals linked list to array. Our parameter is going to be this original student list that we created. And we're just going to write a quick for loop. Let's say I equals 0, I is less than stud array dot length, and I plus plus. In order to, I got to put an int, I forgot to initialize it. In order just to like make sure that it works, we'll just do system dot out dot print line, and then probably for every single one, we're going to do this a really quick way. We're going to use stud array I dot get name. And we can do that because every time we access stud array I, we're getting a student object. So this essentially becomes a student object, and then we can just call getName on that object. Now we should get John Doe, Jane Smith, Bob Johnson, Alice Brown, Charlie Lee. Let's go ahead and let's execute this. All right. Oh, did I print that out? All right, let's go ahead. Let me just save. Okay, so that didn't work, and the reason that didn't work is because I forgot to increment down here. So we were just staying at index 0 the whole time. So now that we've fixed that, let's go ahead and let us try that again. Okay, so as you can see here, we have all the names. Yeah, sometimes I make mistakes on coding. It's good for you to see those as well, so that you know not to make those same mistakes, because missing an increment or an incrementer like that incrementer would lose you a point on the IB exam. So anyways, that's how you transfer data from linked lists to arrays. Now, let's go ahead and let's look at our next method that we're going to write. And we're actually going to be writing the same method, but we're going to be using something called an iterator. So I'm gonna say public static student, and we're gonna say iterator linked list to array, and then our input is going to be linked list student and student list. Now, before we write this method, let's briefly go over what an iterator is and why it is important. And what do we have an error right here? Okay, there we go. All right. So let's go back to our slideshow. Okay. Now, an iterator is basically an object that allows you to traverse the elements of a collection one at a time. So it basically, the whole point of having an iterator is to allow you to iterate through an object easily and safely. So it's supposed to allow for safe modification of the collection during iteration. And it's also a sort of abstraction. So you can access elements of a collection without really dealing with that collection, or in this case, linked list itself. So that being said, let's go ahead and let's see what this actually looks like in code. The reason we want to learn about this is because it may come up on the IB exam, and I have seen it on mark schemes. So really quick, we're just going to write a method involving iterators so that you have an understanding of what that looks like. Okay, so basically how this is going to work is we're going to write this same method, but using iterators. So we're just going to copy this code right here and put it right down here. And now where the difference is going to come into play is we're going to create an object called a list iterator. So we're creating a list iterator object of type student. And we're going to call that student iterator. That's going to be equal to student list dot list iterator. And similar to how we imported the linked list above right here, that is also another Java library. So we're going to have to do import java.util.list iterator. So let's go back down here. And so we created this iterator. Well, we have our array right here. For some reason, there is an issue with that. Anyways, we've got student list.list iterator. Student list cannot be resolved. That's pretty strange. All right, we'll get back to that later. Anyways, so we've got that. We've created our iterator. And now what we want to do is we're going to say while student iterator dot has next. We'll do student current student equals student iterator Next. Now, this is actually very similar to what we see with collections when we're doing work with pseudocode. And what is sort of like, if we look at this and we compare it to this particular block of code right here, we're not using the iterator. The big difference is the fact that here we're interacting directly with the list, versus here we are not interacting with the list. We've created an iterator object that works with our list, but we're not really accessing the list itself on our own. And this is part of that safety and abstraction aspect that makes iterators useful and is the reason why they are used. So now that we've done this, we're still going to need an index. So we're going to say index equals 0. And that's merely going to be to deal with student array. So I got to make that an int. And we're going to say student array index equals current student. Or if we really wanted to, we could just get rid of this. And we could just say student array index equals student iterator.next. And then we're going to increment. And all right, now that we've done that, we can just go ahead and return student array, but not before we fix this syntax error right that's right above here. So notice the iterator, we're not returning the iterator. The iterator is used purely in order for us to work with the student list, which is right here. Okay, and right here we have this really weird error where it says student list cannot be resolved. Linked list student array. It's weird because you have a parameter right here and that's going down right there. Okay, I guess I had to make that capital, so that was the error. Anyways, now that we fixed that, let's go ahead and let's test it out just using our iterator. So we're going to go right here, and we're going to say iterator linked list to array. Let's run that right down here. And it seemed to have worked. So that was a little lesson on iterators. It's not a crucial part, but I have seen it in mark scheme, so just for the sake of completion, it is worth going over, even if it's just in one particular method. Now, our next task is going to be to find and remove a specific object from a linked list. So we're going to create another method. We're going to say public static, and we're just going to have, this is just going to return a Boolean. We're going to say remove by name. And we're going to move a student based on their name from a linked list. That's going to be our first parameter. So we'll say linked list student list, or we can call it stud list, and string name, which is the name of the student we want to remove. Now basically what we're going to do is we are going to remove, we're going to look through the linked list for this particular student. If they exist, we're going to remove them and then return true. Otherwise, we're going to return false, indicating that that student was not found. So we're going to start with int index equals 0. Then we're going to have while index is less than student list.size, or stud list.size. We're going to say student current student, our current student equals student list.get, as we did before, by index. And okay, that is stud list as well. And then we're going to say if current student dot get name is equal to name, which is the name, which is one of our parameters right here. Then we can say student list dot remove, and we can just remove whatever's at that index. Sorry, stud list. I keep getting the two mixed up. Yeah, so stud list dot remove index, and then return true. And this is basically going to stop the loop as soon as we found. This is like assuming that there isn't someone with the same name in that linked list. But once you remove that name, we're just going to stop the entire function by returning true. Otherwise, if we go through the whole linked list and we never find that particular name and return true, we're just going to go down here outside of our while loop and return false. So let's go ahead and let's test that out. We'll go right back up here. And we're just going to get rid of this stuff right here. So if you look at our, so we're going to do remove by name. We're going to put in our original student list as a parameter right here. I'm just going to exit this. So we'll leave student list as a parameter. And then we're also going to put in the name Jane Smith. We're going to remove Jane from the linked list. And we need to say Boolean removed. We'll say Boolean found and removed, or was found and removed. Correct variable naming. And we got student list. That's weird. Cannot be resolved. Okay. Remove by name. Let's remove by name. This is our parameter. And why is it not letting us use student list up here? Okay, maybe I did something wrong with the spelling. But I'll just type that and I'll just say Jane Smith. Can we still have an issue right there? Insert to complete expression. Okay, we'll come back to that in a second. But okay, I guess that was just a really weird minor issue. Anyways, so now we've done that, what I also want to do is I want to display student info so that we can actually see that that particular person was removed from our linked list. And we'll also just print out out.print line was found and removed. Okay, cool. So now we've done that, let's go ahead and let's run this and just see what happens. So we've got this right here. Do you have any problems? No. I think we made the same error we made before. Okay, we didn't increment the index. Okay, so if that statement isn't necessarily true, what we need to do is, all right, this still needs to be in the while loop right here. This is our if statement. This is for a while loop. We're just going to do index plus plus and just keep going. Okay, cool. So keep that in mind. Don't forget to increment. So let's go ahead and let's just give that another try. Okay, and as we can see right here, we have true because we removed that particular student, and we have everyone except for Jane Smith, which is the one that we wanted to remove. Now, the last function, or the last method that I want to write is going to be one that combines two linked lists into one linked list. Now, I actually put this here because I did see something like it on the exam, and I just want to cover all our bases. So it's just kind of an interesting exercise. It won't take too long. So we're going to say public linked list student equals or combine linked lists. And we're going to have two linked lists as our parameters. So we're going to say linked list student student and list 1, and then linked list student and list 2. And then we'll just sort of do that. Okay, so we're going to be returning a large linked list with both of these in them. And so we're going to create that linked list. We're going to say linked list student and combined list equals new linked list. And we're just going to systematically use, well, okay. There are two ways I would do this. For me, actually using an iterator would be easier, but I think we're just going to go through, we're just going to use two indices. We're going to do int index 1 equals 0. And we're going to say, we're going to go through the first linked list. So we're going to say while index 1 is less than list1 dot size. Keep in mind these could both be different sizes. Then we can say combined list dot add, and yeah, we're just going to do list1 dot get and then index 1, and then we're going to increment that. So we're going to say index 1 plus plus, and we're going to say while index. We're going to do the same thing for the next one. We're going to say int index 2 equals 0, while index 2 is less than list2 dot size. Then go ahead and yeah, just combine list dot add. Ooh, I see we have an interesting issue with the index right here. Now I want to go through every single. Okay, actually no, we don't. Never mind. Add list2 dot get index 2. Then once we're done, we just want to return. Oh, we need to increment index 2 again. Learning from my mistakes. And then we're just going to return combine list. Now I'm not gonna test this one out, just because it would just take a long time to set up this test. I need to create a new linked list, and then I need to check whether, and I also want to create some new objects and then check whether they're all in the same list. But I have tested this in my demo, and the logic is sound, which I think is really what matters. But that's basically how you would combine two linked lists. So we basically completed all of the tasks right here. And I think the main thing that was important about this is knowing how to add, how to access, and how to remove elements from a linked list. Because those are things that you may have to do when working with linked lists on the IB exam. You saw iterators. Now I want to go over a few other things. So linked lists are doubly linked lists, but I actually have seen them referred to as singly linked lists on exam questions, like this one, for example. So it says it has been decided to use a single linked list named guess to store and manipulate visitor objects. Construct the code needed to instantiate an object guess of the linked list class, which is weird because on the one hand it's asking us to use a single linked list, but on the other hand it's asking us to use the linked list class. So really, if you think about a doubly linked list, the idea is you can go forward and backwards in that linked list. I would say that as long as you don't try to go backwards, you don't try to go in the opposite direction of linked lists, then you can still use a linked list class, but then abide by the sort of qualifier that's a single linked list. And it's right here, it says construct the code for the method penultimate that returns the second to last element in the linked list guess. You may assume that guess is locally accessible. If you look at this code as well, there's nothing that really corresponds to the fact that it's specifically doubly linked. So if you see this, don't worry about it. If it's asking you to work with a linked list class, you can use all the methods that are available in the linked list class, as long as you aren't really doing things that would be specific to a doubly linked list. And now that we have kind of gone over the coding aspect of linked lists, we're going to go over linked lists pros and cons versus arrays. And we're going to compare it to something called array lists, but actually I think we're probably going to go over array lists themselves before we look at this. So for now, let's just look at the pros and cons. And generally, when we're talking about the pros and cons, we're comparing linked lists to arrays, because most of the times when you see problems in the IB exam that are looking at linked lists or asking about the advantages and disadvantages of linked lists, it's generally in comparison to arrays. So right here, some of the pros are going to be dynamic size. So arrays are static data structures, while linked lists are dynamic. So we can grow or shrink them in size without having to create a new data structure and like re-specify the size. We have easier insertion and deletion because rather than having to move around whole blocks of an array in memory, we can just point to a new node or remove pointers to a node that we want to delete. Linked lists are more efficient because we're only allocating elements for the nodes in those linked lists wherever they're available, versus with an array, for example, if we specify an array of 10 elements, then we're allocating 10 spaces in memory for that array, regardless of whether they're used or not. With linked lists, we're only allocating nodes, or only allocating spaces, or really addresses in memory as they're needed, which makes linked lists more efficient. Moreover, as we'll just see here in a second, linked lists are really versatile because we can actually use them to implement stacks and queues. So we can use them to implement other data structures that may be more appropriate for our use case. Now, some of the cons of linked lists are access time. So we can't access well, I guess this isn't really true for Java linked lists, but in general, the idea is that I guess maybe we're not seeing this in our Java code, but to find a specific element at an index in a linked list, we need to like iterate through the linked list, versus in an array, we are actually directly going to a specific element. So again, with the get method, we don't really see this, but it does take longer to access a specific element in an array than a linked list. Now, while linked lists are more efficient, each individual node is taking up more memory because we're using pointers, which aren't used in arrays, and pointers themselves take up more memory than a single array element. And finally, linked lists can often be more complex than arrays and difficult to implement and debug, just because of having to work with pointers, which you guys don't really see this, but if you ever work with like C programming, then you have to work with pointers themselves. It's just an absolute nightmare. Now, that being said, let's go ahead and let's look at some ideal use cases for linked lists. So two ideal use cases right off the bat are queues and stacks. So a linked list can be used to implement a queue where the front of the queue is represented by the head of the linked list, and the rear is represented by the tail of the linked list. And additionally, we can use a linked list to implement a stack, where the top of the stack is represented by the head, and the bottom of the stack is represented by the tail. And this is really just dependent on like what order in which we're putting things into the linked list. And finally, it's ideal to use linked lists for large data sets because we can dynamically allocate memory. So we don't need to worry about having a fixed size if we want to add more data to a particular data structure, or we have a use case where we need to be adding additional data without exactly knowing how much, then a linked list can be ideal. Now, that being said, now what we're going to do is we're going to move on to array lists, which are very similar to linked lists, but have some differences, and we'll revisit this comparison next. Okay, so now let's talk about array lists. So with array lists, there are 4 basic tasks that we want to be able to accomplish. And I'm not going to spend a lot of time on this and array lists in general, because of the fact that the syntax is virtually identical to linked lists. So let's just go ahead and take a look at the code. So right here, this is our array list code. This is our demo. And the only main differences are really we had to import array list. And instead of linked list, we had array list with the data type. So this is the main difference. Everything else works pretty much the same. Like if you look at the syntax for array to array list, emplist is an array list, and we're just using the add function or the add method in order to add elements from an array into an array list. Similarly, right here, we can use the get method on an array list. This is an example of using an iterator. Again, that works exactly the same way with an array list. So there's really no syntactical difference between array lists and linked lists, with the exception of how you actually just create and initialize an array list. So that being said, let's go back and take a look at what the actual differences are between array lists and linked lists, because I have seen that come up in certain questions. And moreover, it's just worth noting that I have seen specific questions that have asked for answers to be written using array lists, But again, if you know linked lists well, that shouldn't be a problem. Now looking at the differences and the similarities, so we have array lists on one side and we have linked lists on the other side. Now, array lists are dynamic arrays as opposed to static arrays. So with static arrays, you really need to specify the size ahead of time. The array lists, you don't need to do that. You can add, you can remove, you can do pretty much everything you can do with linked lists. But they are arrays. Unlike linked lists, which are actually just doubly linked lists with nodes and pointers. Now, accessing individual elements in array lists is a lot faster because we can go straight to an index and access it there. We can't do that in linked lists. We actually need to iterate through the linked lists until we find our element of choice. That's why we have that get method. We also have a get method with array lists, but it's just faster. Like they're doing different things under the hood. Inserting and deleting is slower with array lists than linked lists because every time we want to add something into an array, we need to move all the elements. We need to move all the elements in the indices below it over one space to another address, and then we need to move all the elements that are above it, which have indices greater than that, to other addresses as well. So it's much slower to insert stuff into array lists and delete stuff as well than with linked lists, where we're simply changing pointers. And with array lists, we kind of have the same issue that we have with arrays, where all of the elements are contiguous, so they're all next to each other. We're not necessarily going to have empty elements like we did before, because this is a dynamic data structure, but they're all together in memory, versus with linked lists, they can be spread out throughout the RAM, and each node just points to the next node via a pointer. Now, array lists are ideal for the random access of elements when the number of elements is known in advance. So particularly if you want to access a specific index, array lists can be faster than linked lists. But if you have frequent insertions and deletion of elements, and we're looking at a situation where the number of elements is unknown, I don't know that this one is really that important, but with frequent insertion and deletion of elements, given that use of pointers, linked lists are going to be the better choice. So basically array lists have very similar syntax. You need to know what they are, and you need to know what the differences are in terms of the mechanics and how they are dealt with by the computer. But there's not really any specific coding or syntax differences that you need to worry about. So that being said, let's move on and talk about 2D arrays. So 2D arrays, you know how 2D arrays work. You've seen it in topic 5. What we're going to do is we're going to go ahead and get into some coding tasks involving 2D arrays. And then we are also going to just talk about what the ideal use cases are for 2D arrays. So let's go ahead and let's get started. So the first thing I want to do is I want to create a 2D array, and I want to initialize it. That's our first basic task. So I'm actually just going to copy that from the other demo code I wrote because it just takes a long time. Then I'll go through what the syntax looks like. So 2D arrays, we have rows and columns. So what we're going to do is we're going to so normally actually on the IB exam, you'd have a 2D array of objects, but that's like creating that many objects and populating a 2D array is just quite tedious. So I'm just going to go to a more easy to approach example where we just have a 2D array full of integers. And we're going to declare that it is a 2D array of integers by having two sets of braces here, followed by the name of the 2D array. Then we're going to initialize it using curly braces, but it's going to have a similar structure to just a regular 2D array. We have rows and columns where this would be like 0, 0. This would be like 1, 1, 2, 2. This would be, let's see, 0, 1, 2, 3. This would be like 3, 1. And this is just basically how we're going to initialize our 2D array. Now, that's creating and initializing a 2D array. We want to do some more interesting things. We're going to access a specific position in a 2D array, insert values into a 2D array, and calculate the average of values in a 2D array. Now, this isn't a dynamic data structure. This is a static data structure. So we're actually going to be, we're just going to be focusing on accessing and getting some data about the values as a whole in a 2D array. We're not going to be removing anything or adding anything to these. So that being said, let's go ahead and let's start with a method. Well, first of all, if we just wanted to access let's just say we wanted to print out some element, right? System.out.print line. We could just do grades, and then we could do like 1, 2, for example, and let's just give that a try. So let's go ahead and run that. All right, and right here we just have 73. So that's going to be on row 1, so right here, and then 0, 1, 2, and that's going to be this element right here. That's just how we access an individual value, okay? So the next thing we want to do now is we would like to actually insert, well, okay, even inserting a value into 2D array, with this particular scenario, we're talking about just changing a particular element. So we might just do, say grades 1, 2. It's going to be equal to 23 instead. And now that we've done that, we can go ahead and run that. And we're just going to get 23 right here. So it's basically just like setting and reading a specific element from the 2D array. And now what we're going to do is we're going to calculate the average of values in a 2D array. But before we do that, we're going to write a simple method just to output all of these values one by one, so in a sequential fashion. And that is just so we can see how we iterate through 2D arrays. All right, so let's go ahead and we're going to do the things in the same format as we did before. So we're going to say public static void, because we're just printing something out, output grades. And our parameter is going to be a 2D array called grades. And we're going to have to use our nested for loop, which we have done using pseudocode, but we haven't yet done using Java. So we're going to do for int I equals 0. I is less than grades.length, which is really just referring to the rows, and I++. So now that we've done that, we're going to iterate through each individual row. So we're going to do for. We're going to have we're going to say for int j equals 0, followed by j is less than grades I dot length, and then j++. Okay, so now that we've done that, we can just go ahead and I'm just going to close this up for a second. So we can just go ahead and we can do system.out.println. Then we can do grades I, j. Again, the difference is really is not really, like there's no difference in logic between the way we do things in Java and from pseudocode, but it's just understanding, it's just useful to see this block of code and syntactically what this looks like. So let's go ahead and let's execute this function. So we're just going to say output grades, and then we're just going to have grades as our parameter. Let's go ahead and run that. And yeah, we'll basically see every single value in sequence one by one. And what we want to do is we're just going to take this and we're going to just sort of do something a bit more complex. Now what I want to do is I want to calculate the average grade. So we're going to be iterating through, but just doing some other operations simultaneously to calculate the average grade. So I'm going to say public static void get average grade. And I'm going to have the parameter as grades again. And now that I've done that, what I'm going to do is I'm going to first create an integer to hold the sum. Because what I want to do is I want to calculate the sum, and I want to go ahead and I want to divide that by the number of grades. We'll say int grades equals 0. or int count rather, equals 0. And then I'm going to have a 2D array. So I'm actually just going to copy paste this because it's lazy to write that again. And then we're going to close our braces right here for the first one. Let's do that, and then we'll just do that. Go to 2D array, and then what we're going to do is we're just going to say, or rather code, sum equals sum plus grades I, j. And each time we iterate over a specific element, we're going to increment count. And actually, I think we're actually going to return the average as a decimal. So we should change our return type to double right here. But once we've done that, we can create a, so this is outside of our last for loop. We can say double average equals sum divided by count. And then we can return the average. Now let's go ahead and let's run that. So we'll just have get average grade. Let's go ahead and run that. And did that output anything here? That didn't actually output anything. Oh, I guess we actually need to print. We need to like get that in a variable. So we're going to say double average. We're going to store that in a variable rather. Equals get average grade. And then we're going to print out average. Cool. Okay. Cool. We got an average of 81.0. So that's basically, like, I would say that if you understand how to iterate through a 2D array in this fashion, and you understand the fact that that first loop is going through the rows, that's 0, 1, 2, 3, 4, and that second loop is going through the individual elements in the row, then you're pretty much sorted. Like the logic, like linked lists don't exist in pseudocode the same way that 2D arrays exist in pseudocode. 2D arrays, like there's not really that much new syntax to learn besides what naturally goes along with Java. Obviously, you just need to understand how it looks when working with 2D arrays instead of 1D arrays. But if you understand this logic in pseudocode, then it's not a dramatic leap to do this with 2D arrays, and there's not a lot of other there's not like a significant conceptual difference. So that being said, let's go over and let's talk about what some of the ideal use cases of 2D arrays are, because there are questions about whether a specific situation would or would not be ideal for the use of 2D arrays. Now, just some basic examples are image processing. So what 2D arrays are good at are representing a table of data or a grid of data. So image processing can be a great use because we can represent images as 2D arrays where each pixel is a particular element in the array. And once we've taken each pixel or the hex code that describes the characteristics, or rather the color of each pixel, into a 2D array, then we can do some manipulation on this, such as resizing, rotation, filtering of that particular image. So 2D arrays are heavily used in image processing. They're used in games. They can be used to represent game boards or game maps, which are going to be grids. And each cell or element in an array could represent a specific location in a game world. This allows us to manage what's going on in the game and also kind of detect where an object may be in the map or a player may be in the map. And the other one might be data analysis, because 2D arrays are effectively representing a table with rows and columns. It can be very useful for feeding data into algorithms for more complex processing and statistical analysis. So that being said, let's move on to stacks. Okay, so with stacks, there are 4 basic tasks that we want to be able to accomplish. Now, the cool thing about stacks is that we actually do have a library built into Java through which we can create and initialize a stack and then manipulate it. And it also works very similar to the way it did in pseudocode. So this should be relatively easy to grasp, but we're still going to go through and we're going to write a few methods to accomplish these tasks so you understand how things work in Java, not just in pseudocode. So let's go ahead and let's get started with that. Okay, the first thing I'm going to do is I'm going to create a new stack and initialize it. And this stack is going to be a stack that contains students, similar to our previous examples. So actually, before I do that, I need to import the library. So I'm going to say import java.util.stack. And now what I can do is I can say stack student. So stack with student objects equals, well, we gotta say student stack, I guess. We have to give it a name, is equal to new stack. So there we go, we have a stack with student objects called student stack. And we've created a new, we've instantiated that basically. Now what I want to do is I want to put some student objects in the stack. I'm just going to copy that from my demo code because it's pretty self-explanatory and it just takes a while. Basically, we're going to do student stack.push. And you should recognize this push mode or this push method from pseudocode. And each time we're going to create a new student object and push that into our stack. So another way to view this as well is we could just say John equals this statement right here. And that would work as well, although we should probably give that a data type, and there we go. So what we're doing right here is the same thing as what we've done all the way through here. The point is we are creating 5 student objects and then we are pushing them onto this stack right here. So now that we've done that, the first thing I want to do is I want to display all of the elements in the stack. And I think that was right here. Well, we'll get to this part right here, but I think it's worth writing a method to be able to display everything in the stack to begin with. So that way we can go ahead and we'll be able to, at any point in time, see what's in the stack. So what we're going to do is we're going to write a method called, we'll say public static. This isn't going to return anything. This is just going to output all the elements in the stack. We're going to say public static void display stack. And then we'll say stack student, and we'll just call that students. Now what we're going to do is we're going to create another stack called stack student. Well, it's not called stack student, but it's going to be called temp. And the reason we're going to do that is because in order for us to be able to access each element in the stack and display it, we're going to have to pop it out of the stack. But we need to store all those elements somewhere in a different stack because after we've popped them all out and printed their values, we want to put them back into the stack in the same order in which they were popped out. So this serves as sort of a temporary holding area for all of the elements that we're popping and reading out of the stack. And we're going to be using this type of structure pretty often, just because we're going to have different tasks in which we need to get all of the elements, or we need to check all of the elements in the stack, and then put them back in the same way they were. So we're going to say while students, or rather while not students, dot is empty. Student, current student, we'll call it current student, equals students.pop. And every time we pop, we're getting a new object. So if we push all of these into our stack, the first element we're going to pop is going to be Charlie, because that was the last one that we pushed in. So now that we've done that, we can go ahead and print out the information from that particular student, which is what the point of this was anyways. So you can say system out.println, and then we've kind of seen this line before, current student dot get name plus current student dot get grade. Cool. Okay. And now what we're going to do immediately after is we're going to push that into our temporary stack. So temp.push and then current student. So basically the way this is going to work is the last element that was pushed into the stack is going to be popped out, and that's going to be put into the bottom of this temporary stack. The result is actually that when we take everything out of this temporary stack and put it back into our original stack, it's going to be in the same order as it was before. So what we're going to do now is we're going to do while. So basically what we've done in this particular stage right here is we've popped everything out of the student stack one by one. We've printed out its information and then put it into the temp stack. So now what we want to do is we want to take all of the students in the temp stack and then put them back in the students task. Because after this while block, the students task is completely empty and the temp stack contains all the objects that were in the student stack. So similarly, we're going to do while not temp dot is empty. Now let's do that. And then what we're going to do is we're going to pop those out. We're going to do everything in one line here. So we're going to say student.push, or students rather, students.push, and then temp.pop. So we're going to simultaneously pop an element out of the temp stack and then push it into the student stack. And why is that not working? Okay, you have students right here. All right, student, okay, it's kind of a hangover. Okay, so we've done that. And we've got this right here. Okay, everything looks like it should be good. Let's see what error we have right here. Sometimes it's kind of like, okay, let me just backspace. Students. Okay, we'll say students.push. Okay, and then temp.pop. Okay. I don't really know what the error was there, but sometimes weird things happen, and part of it could be Visual Studio Code, or Visual Studio. What I will say is that, as we kind of saw right here, if we just kind of look at the other sort of methods here, there are obviously a lot of methods that can be used with stacks in Java, but oftentimes the questions that involve stacks will tell you that you can only use 3 methods, which are isEmpty, push, and pop. So I would make sure and absolutely try to focus on using those methods unless you have no other choice. And even then, most of these questions should be done just using pop, push, and isEmpty. Okay, so that being said, I think we're good there. We can display everything in the stack. Let's go ahead and let's just test that out and see if that works. So we're just going to do display stack, and then, yeah, student stack, which we have right up here. Let's go ahead and let's run that. Okay, we've got an error somewhere. Okay, right over here. I missed that. Cool. All right. Okay, and it looks like we can see everything right here, with Charlie Lee being the first one to be popped out. So cool. Okay. Now, what we're going to do next, we have a method to display everything in the stack. What we want to talk about next is how we can actually add and remove values from a stack. Okay, well, I think what we're going to start with, well, okay, I guess we're talking about adding and removing values from a stack. We've kind of already done that with push and with pop. That is adding and removing values from a stack. So I think what we're going to move on to is finding the maximum value in a stack, because this means that we need to go through every single element and then we need to figure out whether it's the maximum or not. And this is actually a task I've seen on an IB exam before. So that being said, let's go ahead and let's write a method. And we will call that method public static int maximum grade, find maximum grade. And we're going to do stack. So our parameter is going to be a student stack. And we're going to call it students as we did before. And okay, so what we want to do first is similar. I mean, like, so just like the previous example, we're going to have to take everything out of our student stack and then analyze it. So we're going to go ahead and we're just going to copy this line because we're going to need a temporary stack. So we're going to do that right there. And then what I want to do is I want to basically get the first student in that stack. So student first student equals students.pop. That's going to be our first maximum. Because remember how we find the maximum is we go through the array. So we set our first element equal to the maximum, and then we're going to go through, not our array, but go through our data structure in this case, and then check whether the subsequent elements are greater than our maximum, and if they are, then change the maximum to whatever that is. So we're going to start with the first element right here, and we're going to say int max grade, because these are all integers, equals first student dot get grade. And since we popped this out of our student stack, we also want to go ahead and push it into our temporary stack. So push that in there. Now that we've done that, what I want to do is I'm going to say while not students dot empty. Yeah, I guess it's not is empty. I said is empty before, but I guess both of them actually work. I guess we'll stick with this for clarity. So while not students dot is empty, student current student equals students.pop. And we're going to say int current grade equals current student.getGrade, because ultimately here we want to find the maximum grade. So we'll do current student.getGrade. And now that we've done that, we're going to say if current grade is greater than max grade, which was this one up here, then our new max grade is going to be our current grade. So basically the same way we would have done this in, I guess I need to make that, basically the same way as we would have done this if we were just going through an array and trying to find the maximum value. And every time we do that, after that comparison, what we're going to want to do is we're going to want to push that student object back into the temp stack. So we'll push current student back into the temp stack. And then once we're done, what we're going to do is we are going to take everything out of the temp stack, and we're going to put that back into our student stack. So we have the same stack that we started out with, and we can work with it later. So we'll do students.push and then temp.pop. Cool, okay. And we have a return type of int. We want to return the maximum. So we're just going to go ahead and we're going to return the max grade down here. So let's go ahead and let's try that out. Okay, so we're going to say int max equals find maximum grade. All right, cool. And then we'll just print that one out right there once we found it. Okay, cool. Let's go ahead and run that. All right, and we got 92 right here as our answer, which is apparently the maximum grade. Now that we've done that, this wasn't exactly on our list, but I also do, I'm just kind of improvising here, and I would like to write a method that filters out grades from a stack. So with this stack right here, what I want to do is I want to write a method that will only get the high scores. By that, I mean it will get rid of all elements from the stack that are less than 90. because I think that this is a common task, not necessarily a common task, but I've seen this on past IB exams. So I do think that it is worth going. So let's say that we want to, so we'll say public static void filter out low grades. Particularly on the IB exam, obviously like a low grade is not a 90, but it's just for practice. So we're going to put our stack here, student and students. So we're putting a stack and we're just going to filter out low grades from that stack. So yeah, I mean, this is also a good example of an object reference, because whatever object you put in here, we're going to be editing that particular stack, and the state of that stack is going to change anywhere else that we use it. So anyways, what we can do is we can just do while. So we can just go through the stack while not students.is empty. And what I want to do is I want to create, actually, you know what, I think I do need to create a temp stack here as well. So what I'm going to do right here is I'm going to put his temp stack right here, or temporary stack. And I'm going to go through this, and I'm going to say that I'm going to get this current student. So I'm going to say student current student equals students.pop. And this means that I'm going to pop every single student, regardless of what the grade is. Then I'm going to check if current student.getGrade is greater than or equal to 90. And if it is, then I'm going to pop it into my temporary stack. So I'm going to do temp. I'm going to push it. I'm going to do temp.push current student. Otherwise, it's not going to get pushed. So I should have, by the time I'm done with this, I should have an empty student stack, and I should have a temp stack only with those students that have a grade of 90 or higher. So yeah, okay. So I put that in my temporary stack, and now what I want to do is, of course, I'm just going to actually copy this right here. I just want to get all of the elements out of my temp stack, and then put them back in my student stack. So what we're going to do is we're just going to go back up here, and now we're going to run that. We're going to say filter out low grades, and we're going to put our student stack in there from up here. And now I want to display my student stack. So I'm going to say display stack, student stack, to see what we get. And let's see whether that works. Okay, so you've got Bob Johnson with 92 and Jane Smith with 90 right here. So I guess that worked. Sometimes I improvise things like this on the fly, and I don't know whether I messed them up or not, but looks like it worked. Now, the last thing I want to do is find and remove a value from a stack, which is very similar to actually this filtration thing we just did, but it's going to focus on a specific value. So let's just go ahead and do it anyways. It's good practice. What we're going to do is we're going to do public static Boolean. We're going to be returning a Boolean just to indicate whether that value is found and removed or not. So remove student, and then we're going to have stack students, and we're going to be removing students based on their name. So we'll say string name, similar to what we did with LinkedLists actually. We're going to have a variable right here called found, and that's going to be false to start out with. And then as always, we're just going to need a temp stack or temporary stack. And we're going to say while not students dot is empty. Student dot current student. So we're just going to have this same line right here. And we're just going to get the current name as well. So we're going to say string current name equals current student.getName. And then we're going to say if current name does not equal name, then we're going to push it to our temp stack. So we're going to push everything. We want to remove a student with this particular name. So if we find that student with that name, we're not going to put them on into the temp stack, because the only stuff that goes into the temp stack is the stuff that we want to keep. So we're going to do temp.push and then current student, but only if their name is not equal to the one that we want to remove. So cool. Okay. Now that we've done that, well, also I think what we want to do is if the current name is equal to the name, so that means that's the else condition, we're going to do found equals true. So if it's the opposite of this condition, if it's current name equals name, then we're going to change found to true, because that means that we've actually found that particular student and we're not pushing them into the temp stack. Then now we've got our typical sort of block of code right here. And yeah, that's it. Although I think one thing we need to do is we need to return found. So we're good to go. So what I want to do now is I'm going to go ahead and test that out. I'm going to say Boolean found equals remove student. And I think I want to remove Bob. So we're going to move Bob. I mean, he has the highest score after all, or Bob Johnson. And he probably ruined the curve. So we're going to move that student. And we're also going to just display the stack afterwards so that we know that we did it right. And we can also go ahead and just print out that Boolean. Just, I don't know, just to make sure that works. Let's go ahead and let's run that. Okay, cool. And we have everything here except for Bob. And we have true for found. So that covers everything you need to be able to do with stacks. Really, like there was a similar pattern there where we're taking stuff out of stacks and then putting it back in. That may or may not change. It really depends on what the question is asking you. But that is an easy way to make changes to stacks. Like more complex problems will inevitably involve you having to create a temporary stack. This is just an example of a stack problem. Now, okay, it says a new parking service has been introduced. Staff will park the car for the driver and then return it later when the driver wants to leave. The service will use a narrow parking area surrounded on 3 sides by walls. And so basically, it's creating a stack scenario where any cars behind the required car must be reversed out. For example, car X000011 was the first vehicle to be parked. So to remove it from the parking area, the other 5 cars will need to be removed. So we literally have a stack right here, where this is the element at the head of the stack, or at the top of the stack, and this is the element at the bottom of the stack. As you can see right here, it says the class stack, which contains the vehicle objects, has the following methods. So it has these 3 methods. So it's weird because, like, obviously, like, they know that there is a stack class that we can use in Java, but they're kind of limiting you to only using these 3 methods. And so it says the method staff remove car will remove a vehicle with a specified registration plate, which is very similar to our name example. And yeah, so you just need to write this method to construct the staff remove car. And this is pretty similar to what we did. We have a temp. We're finding a specific vehicle by their registration. They use an equals method. We just use an equals symbol. Doesn't really matter. So basically, they did the same thing that we did. There's some slight syntactical differences, but the result is the same. And yeah, this is the alternate example. So what I want to get into now are we're going to get into some ideal use cases. So there are roughly, these are like 3 of probably the most common use cases that I found. The first is an undo redo functionality. So basically, if you think about Microsoft Word or any application you use, like any editor, there's usually an option to undo or to redo specific actions. And stacks can be used to sort of create this functionality. So each time a user performs an action, such as typing a character or moving an object, that action is added to the stack. And because it's last in, first out, the user wants to undo an action, they can just pop that last action out, and then they can just basically reverse what they just did. And if they want to redo that action, then they just basically pop that back in. The other is for evaluating mathematical expressions. So each time a new operator or operand is encountered, it is pushed onto the stack. When an operator is encountered, the operands are popped off the stack and the operation is performed. So we keep putting values into a stack, and then when we encounter the operator that is meant to operate on that stack, then we can pop them off and we can push the result back in. And then function calls. So basically when we call functions, those all go into a stack, and then they're called in the basically in the order, like in the last in first out order. So the most recent function that's been called is going to be executed, and then we'll move further down. So it says, well, actually, let me clarify that. That's actually only true with recursion. But okay, let's go back. Let's think about just functions in general. So basically each time a function is called, its parameters and local variables are pushed onto the stack. When the function returns, the values are popped off the stack, and control returns the calling function. So I guess there's a few ways. One, I just mentioned recursion. Right here we're talking about parameters and local variables for a particular function. I guess the best way to summarize this would just be that basically stacks allow us to put function calls into a particular order and then execute them in that order. So it allows us to keep track of function calls. And I kind of wanted to go back to this particular question. So right here, it says a stack can be implemented using an array or a singly linked list. Compare the use of these two data structures for creating a stack. So there are a few ways you can kind of compare these. One, you can talk about efficiency and ease of use. So the use of pointers versus having contiguous elements in memory. I would say like another point that you could talk about is being able to dynamically add and remove elements from arrays versus linked lists. Really what it comes down to is singly linked lists are the better solution. But just thinking about the characteristics of arrays and linked lists, there are a variety of ways to come to the conclusion as to, or to be able to compare both in terms of creating a stack. Okay, so now let's talk about recursion. Recursion is probably one of the most challenging topics on the option D HL portion because you, one, actually have to write code in some cases. And two, I think that the recursion problems, like what you're asked to do, goes a little bit beyond just the paper 1 HL exam. Anyways, with recursion, what you're going to need to do is solve problems by writing recursive functions, or well, I would actually say in most cases, even if you're not writing recursive functions, you're at least going to have to explain how you would write a function. So explain a recursive process. And then solve trace tables. And trace tables are relatively trivial. I would say the main, the main aspect is that you'll just need to look at code in Java rather than pseudocode as you would on paper 1. So what we're going to do is we're going to look at about 3 different recursive functions, and we're going to write code for them and then kind of work through how we decide, how we decide what to put in the function. So like, what is our return statement and how we can recursively solve those problems. So before we get started, here's some top tips for using recursion. First, you need to understand that recursion is used when we are repeating the same behavior with consistently changing patterns. So recursion, in a sense, is similar to loops in that you're repeating one type of behavior over and over again, where one or more parameters are changing. Next, I would say the most important thing to do when solving recursive problems is to model the problem with an example input and output. So for example, let's say that you need to write a function to calculate the value of the Fibonacci sequence at a certain integer, which is one of the most common recursion problems out there. You need to put in a value, and you need to basically choose some value n, and then decide what the output is going to be. And then between the input and the output, you can try to use recursive tactics to figure out what your function is going to look like. Next, and kind of relating to number one, whatever problem you have, you need to break it into a set of individual steps. So each time the function executes and calls a return statement, that's going to be an individual step. So break the problem down. Let's say, for example, you have to add up all the numbers from 1 to 6. Each of those addition operations is going to be an individual step that you're going to have to take into account, or that's going to shape what your function is going to look like. Another tip, keep in mind that at least one of the function parameters is going to have to change on each recursive call. So for example, if you have Fibonacci and you have n as a parameter, it's probably going to change. It's probably going to go from n to n-1 to n-2 to n-3 and so forth. And this kind of depends on what kind of problem you're solving. We're going to see a problem later on where that's not exactly the case, but for simpler problems, this applies. And finally, understand that the base case is where the recursive calls will stop. So the base case is usually if you've seen if n equals 1, or it's basically that condition when you stop recursing. Is recursing a word? When you stop recursing. So if these don't make sense, we're going to go through a few examples and we're going to apply these tips so you get a better understanding of how to write recursive functions, or at least explain recursive processes. Now, the first function we're going to work with is going to be factorial. Now, factorial is usually that one you've seen with an exclamation point. So for example, 4 factorial is going to be 4 times 3 times 2 times 1. 5 factorial would be 5 times 4 times 3 times 2 times 1. So we're going to start by modeling this problem, and we're going to choose the value n for, or we're going to choose the value 4 to be our n to start out with. And we know that if factorial 4 is n, then we should get, or if factorial n has an n of 4, then our result should be 24. So what we're going to do is we're going to actually break this down into the individual steps in order for us to get a solution. And when we think about the individual steps, especially since we're working with recursion, it's important that our function is a part of those individual steps, okay? And the way we can think about this is that 4 times factorial 3 should give us 24, because factorial 3 is going to be this part right here, right? And then 3 times factorial 2, and the reason we have 3 here is because in this case, that makes n 3. And in this case, n was 4, right? So 3 times factorial 2 should give us 12. And 2 times factorial 1 should give us 2, right? And this right here essentially represents factorial, this is going to be factorial 1. This is going to be factorial 2, factorial 3, and factorial 4 right here. So right here we have individual steps involving our function that would give us, ultimately that would give us the value that we want. And if we go through these steps, we can generalize into a value of n times factorial of n minus 1. Because to get the factorial of n, which is 24 right here, we had to do our n times n minus 1. To get the factorial of n right here, assuming n was 3, we had to do n times n minus 1. And this and so forth. And really right here, these matter because right here, we used the function factorial 3. So this initiated all of these other steps right down here. Now, that may be a little confusing, but we're going to go ahead and write some code, and we're going to trace this. And maybe once you do that, it'll make a bit more sense. So let's go ahead and let's write the code in order to solve this problem right here. Okay, so right here we have a typical just main function. And we're going to start by writing our factorial function. So we're going to say public int factorial. Because remember, factorial, we want to, whatever number is our n, we're going to multiply it by every number that comes after that. So for example, right here, factorial of 4, we did 4 times 3 times 2 times 1. Factorial of 3 was technically 3 times 2 times 1. So we're going to say int factorial n. Obviously, we're going to be returning an integer, and our input's going to be an integer as well. So we're going to do that right there. And we're going to have a base case, which is where our recursive function is going to stop. We're going to have a return function. Now, we've already decided by looking at this logic right here that we want to return. We're going to return, what we'll call this our recursive call, that we are going to return n times factorial n minus 1. Because that's effectively what we need to do to get this right here, which initiates the chain of other factorial calculations, right? Because this was 2, and this right here was, well, so factorial 3 would have been 12, and then factorial 2 right here would have been 2, and multiplying those, we eventually would have gotten 24 right here. So this initiated that chain, which is why we have this right here. So that's n times factorial n minus 1. Now we're going to keep calling. So if you look back to this example right here, we want to keep going until I would say n equals 0. So we can say, or really, I guess, so we could have factorial 1, but once we subtract this and we get to n equals 0, that's where we want to stop. So we're going to do if n equals 0, return 1. Because factorial of 0 is actually just 1, in fact. And there's nothing else, there's no multiplication that we really need to do there. And that's actually basically our function. And that seems really simple, but let's go back to our slideshow. Let's go ahead and let's actually just trace how and why this works. Okay, so let's pretend that our n is 3. We've kind of already done this before, but I mean, I think we don't really want a huge example, right? So factorial 3, and we're going to look at this function right here. Or actually, right here, it's the same as what I did earlier, but the orders of n and factorial n minus 1 are reversed, which is actually not a big deal. So we're going to start with factorial 3. That means that our first return statement, we're going to have return factorial 2 times 3. And then next we're going to have, I'm just going to write r for return because it's a bit tedious. So we're just going to have return factorial 1 times 2. And then we're going to finish off with return factorial 0 times 1. So factorial 0 times 1. Okay, and then we can actually work our way backwards because 0 is actually the base case. So for this one, we're going to have 1 times 1. So that means that factorial 1 is just going to be 1. Then we're going to have 1 times 2. And that means that factorial 2 is just going to be 2. And then we're going to have 2 times 3, which means factorial 3 is just going to equal 6. And that gives us the right answer. It may seem a bit messy, actually really just in my handwriting. That's basically how we get to the answer, following the same logic that we talked about before we wrote the code. So that being said, let's move on to our next example. Okay, so the next recursive function we're going to look at is one that just actually calculates the power, or the power of a base. So for example, right here, we have power, where an int base is one parameter and exponent is the other parameter. So for example, if we wanted to do 3 to the power of 4, we'd have 3 as our first parameter and 4 as our second parameter. And that would give us 3 times 3 times 3 times 3, which is 81. Now, kind of if you remember earlier, one of these parameters needs to change, and we need to break this up into individual steps. And those individual steps in a recursive function are going to be using the function itself. So if we follow a similar process we did to the previous question, we can do 3 times power of 3, comma 3. Because like basically we're going to have whatever 3 times 3 times 3 was. 3, so basically 3 to the power of 3 times that final 3. And that should give us 3 to the power of 4. So this this itself can kind of give us the answer. But if you kind of extrapolate this one down right here, that's just going to be 3 times power 3, 2. 3 times power 3, 2, so 3 to the power of 2. And then that's going to follow down to 3 times power 3, 1. So really just this last 3 right here. And that's going to give us power 3, 2, which was this one right here. So if you look at these, we can look at a particular pattern. So the base is always going to stay the same. We're always going to have 3 times something. In this, I suppose that in terms of the function itself, that would just be base times something. And then we're going to have the power function with, again, the base staying the same and the exponent reducing by 1 each time. So the exponent is going to be the parameter that's going to change. And when you think about that particular parameter changing, it's kind of similar to decrementing in a while loop. So now we've kind of walked through this logic. Let's go ahead and let's see how we would actually write this function, because we haven't really taken the base cases into consideration yet. Keep in mind, just to review, this is the base case right here, which stops the function from making recursive calls. Now, what I want to do right here is I'm going to say public int power int base int exponent, and then I'm going to have well, okay, so obviously, like looking from right here, this is going to be our recursive component. So we're just going to return base times power, and then base exponent minus 1. But we need to decide like where this is going to stop, right? And I think that there are a couple of valid stopping points. So first we could say if exponent equals 0, then we can just return 1. So yeah, if we ever get to the point where the exponent is a 0, we can just return 1. And I think that's a pretty valid base case. The other thing we can do, and this is just going to stop the function from running any further right away, is we could say if base equals 0, return 0. It's not exactly a base case, but I mean, I think it makes sense that if the base is 0 to just return 0 right away, because if the base is 0, then every single, regardless of what the exponent is, we're always going to get an answer of 0. So what I didn't do in this one, and what I want to do right here, actually, is go ahead and try this function out and see whether it works. So let's go ahead right here, and we'll just do, I think we need to make this static, actually, just to be able to run right in here, not for any reason that's relevant to the IB exam. And we'll just do power 3, 4, and just see what happens. Make sure we don't need this anymore. That's from a previous example. Cool. All right, let's run that. Oh, I should probably print that out, actually. I need to create a variable. We'll do int answer equals power, and then system.out.println, and then answer. Cool. Okay. Cool, and we got 81 right there, which is exactly what we expected. So now that we've gone and we've sort of figured out how to write this in Java code, similar to the previous example, let's go trace it just so that you guys get a real, like, clear understanding of how this works. Okay, so right here, we have our function that we wrote. Initially, I had this if statement right here, which actually doesn't make much sense now because, I mean, it's kind of redundant. Like, if we just went through our recursive function, we would still get this right here. So regardless, what we're going to do is we're just going to go ahead and trace power followed by, let's say, 2, 3, just to kind of keep it short. So what we're going to do first is we have our base of 2, and we're going to check, well, we're going to check our exponent. Our exponent is 3, and our exponent doesn't equal to 0, and our base doesn't equal to 0. So we can go ahead and we can return 2 times. So we're going to have 2 and then exponent minus 1, which is 2. So actually, let me just go ahead and it's going to be power. And then 2, 2. So then we're going to calculate this right here. And we're going to just write R for return. So we're going to have R right here. So it's going to be R. The base is 2 times power 2, 1. And I suppose this actually would have made it shorter right here, but we're just going to stick with what we have. And then we're going to go right down here, and we're going to have R 2 times power 2, 0. And we know that the exponent is 0, that we're just going to return 1. So that means that this is going to be 1, and power of 2, 1 is just going to be 2 times 1. So that's going to be 2. And that means that power 2, 2 is just going to be 2 times 2, and that's going to be 4. And then we're going to have 2 times 4, and that's going to equal 8. So that's how that particular function works. Again, sorry for my terrible handwriting. Like, I hope this makes sense, but I'm doing this on an iPad, so. Okay. So let's go ahead and let's go to our last example, which is a bit different than all of the others. Okay, so our next function is going to be called isPalindrome. And with isPalindrome, we're just going to input a string, and we need to check whether that string is a palindrome. Now, if you've never heard of it before, a palindrome is a word like kayak that looks the same forward and backward. So if you took kayak and if you took all of the letters, so if you like reverse the order of all the letters, you'd still get the same word, and that's what a palindrome is. And we need to use recursion, which means that we need some repetitive behavior until we hit an endpoint. And remember in recursion that we're repeating the same behavior with different parameters. So we're going to have to use some repetitive behavior to go through this particular string, or really any string, and decide whether it's a palindrome or not. And if we were to think about like what being a palindrome really means, to make sure a word is a palindrome, the first letter has to be the same as the last. So that means this letter has to be the same as this letter. And then the second has to be the same as the second to last. So this letter has to be the same as this letter. And then this one right here doesn't really matter because it's just in the middle. But that process would have to be expanded if we had more, if we had a larger word, basically. And basically the point we're going to stop, our base case, is going to be when we get to the middle. And there's no other letter to compare it to. So there's either, so it's an even number of letters and there's just nothing left, or there's an odd number of letters and there's only one letter and we can't really compare it to anything. So basically we're going to be comparing these, and then this is our base case right here. So that being said, let's go ahead and let's write some code. I know I kind of showed you the trace earlier, but I'll go through and we'll write the code and I'll explain to you how it works. So I'm just going to get rid of these because we've already kind of gone through these right here and we don't need them again. Do that. Ooh, I should probably keep that one right there. Okay, cool. All right, so I'm back in my main driver class and we're going to write this function called public boolean isPalindrome. And if I didn't mention it earlier, if it's a palindrome, we're going to return true. Otherwise, we're going to return false. By the way, this one's actually taken directly from an IB exam. And the difference is that in the IB exam, we didn't actually have to write the code for this, but you had to explain how it would work. So you basically had to say, you had to say, okay, we would look at the first character and the last character, and then so on and so forth. So you kind of had to know that you can actually break these down, or you can check individual characters in a string. But basically what we're going to do is we're going to start with our sort of first scenario right here, where the first letter has to be the same as the last. So we're going to say if a word dot char at 0, meaning the first letter, the index of the first character, equals 0, or we're not going to make that I, equals word dot char at word dot length -1. So again, we can get the characters in this string using the same sort of scheme that we do with arrays, right? So 0 is going to be the first one, and length -1 is going to be the last one. So if the first letter is the same as the last letter, then that's kind of the first step to it being a palindrome, right? And every single string has a first and a last letter. So it's not something that's really going to be subjective based on the length of the word. So this can kind of be where we start out, right? So if this is true, then let's go ahead and let's check whether we have a palindrome. So if this is the case, what we're going to do is we're going to keep going down the rabbit hole. We're going to say return isPalindrome. But what we're going to do is we're going to check whether this is true for a string that only includes that only includes the second to last character that only includes the second character until the second to last character. So we're going to say word.substring. We're going to create a substring. Actually, let's just keep our kayak example right here just to make it kind of clear. So right here, what we did is we checked whether k was equal to k. So now what we're doing is we're creating a whole nother string, and we're creating that other string is just going to be IAC. So from the second letter to the second to last letter. So word.substring 1 and word.length -2. Let's make sure all our parentheses add up right here. Okay, we still need that. And this kind of works. We don't really need to go any further than this because, like, let's say we had a longer example. So let's just pick an incorrect one. Actually, say we had congratulations, right? Actually, let me just find a longer example real quick. Okay, a longer one is going to be race car. So what we're going to do is we're going to go to the first and last one. We're going to check whether those are equal to each other, and if they are, we're going to make a string out of these two. And then we're going to put it back into the function. And we're going to do the same thing again. So then we would check whether A and A is equal. And then we'd make a string out of CEC. And then we would check whether C and C is equal. And then we'd hit our base case. So this is all we really need to do. However, if this first case is false, right away, what we can do is we can just return false, because obviously if that first comparison is false, then nothing else is then it's not a palindrome, right? And also subsequently, when we break these into strings, if we have false, so if any of these aren't equal at any moment, then we can just return false. Because every time we break these down into smaller strings, the first and last character have to be equal. Otherwise, that word, the beginning word, it just isn't a palindrome. Now, we're going to account for our base case, which is like right here, E, right? We just have one letter and we can't compare it to anything. So we're going to say if word dot length is less than or equal to 1, then we're going to return true. Because if we've gotten to this point right here and we still haven't returned false, that means it's a palindrome, right? So either this point, or if we have a word where it has an even number of letters and we have a length of 0, if we got to that point, then we can return true. And that's how we write the code for is palindrome. Now again, just to reinforce understanding, what we're going to do is we're going to go trace it, probably with race car, actually. Okay, so let's trace this function. We're going to say is palindrome. And then I guess we'll put in race car, even though I can't really fit that here. So if we go to this function, we're going to check what the word length is. And then we're going to check whether the first and last letter are equal to each other. And they are. So the next thing we're going to do is we're going to return is palindrome. And then ACE ka as a string. We're going to do the same thing. We're going to check whether the first and last letter is equal, which it is. And then we're going to return is palindrome. And then seek. Okay. And then we're going to go through again, and we're going to check, so basically what we're going to do is we're going to return, so we're going to return E, because that's actually going to match the index of, that should match the index of 1 from this letter. It's also going to be the length -2, because the length is going to be 3. So we're just going to return E. And then we're going to hit our base case because the length is going to be 1, and we're just going to return true at that point. And so that's how we know this is a palindrome. Okay, so this recursion question is, so it looks like it could be on an HL paper 1, but there are a few layers of complexity that make it different. For one, it's written in Java. But also, if we look at this function right here, so we're starting out right here with the typical method definition. The name of this is recursion X. We're going to refer to it as func from now on because it's shorter. And now we see if X doesn't equal 0, we're going to print out the parameter X. So that's going to be our first line right here and here. And then we're going to make a recursive call, but we're not actually returning a result this time. So we're not doing return recursion X or something like that. And that's going to be our second line, and that's where we're going to run into the most trouble. And then our third line, which is also just going to complicate things, is going to involve printing out the parameter after we've already called a recursive function. So we're going to go through and we're going to fill out this trace table, and I'm going to explain why it is that things are the way they are. So first we start with 3, and then we're going to hit line 1 in our if statement, and we're going to have the output. So that's going to be 3 right there. But then we're going to need to make a recursive call, right? So our first recursive call is going to be func, which is actually just recursion X2. Now, if 2 is our parameter, that means that in this column where it says parameter passed to method, we're going to write 2, and then we're going to print out 2. Okay. Now, after we've printed out 2, we're going to be calling func1. And that means that we're doing this again, right? We're passing 1, and then we're printing out 1, which is just line 1 inside our if block. And then we're going to print out func0. And when you print out func0, we are going to pass the parameter, but we're not really going to have any output there. Now, one thing that you need to keep in mind is that when we called recursion X2 right here on line 2, so this one right here, that stopped the function at this point. So we could never print 2 out twice. We couldn't print out this third line. And the same thing was true in here, right here. We stopped at recursion X1 right here. And we actually just didn't do anything right here with func0. That was sort of like, blah. But anyways, so we have func0, we are doing nothing, but if we have executed function 0, that means that we can move up a level back to so basically that means that in the function, so in the situation where we have recursion x1 or func1, right? That means that this line has been completed right here. So we can go ahead and we can actually print this line in this function right here. So we're going to output 1, okay? Now, if recursion 1 has been executed, that means that in the scenario where we have recursion x2, also known as func2, that means that this line has been executed there. So then we can go ahead and we can print out this line in recursion x2. And then in recursion x3, coming all the way back to the beginning, so if you go back to recursion x3, right here we had recursion x2, right? So that means that this has been executed, and now we can go ahead and we can print out this right here. So it's interesting because we're not returning anything, but we're calling a recursive function, and this line right here, this line 2 in the if block, is holding up the functionality of not only our function of the first parameter, but every subsequent recursive call that we have. So we end up printing out our output 3, 2, 1, and then printing it back out in reverse, because we're essentially working our way back up the chain once those recursive functions are successively being called. And hence, this is the mark scheme, or this is the answer. So yeah, it's a more complex question than you're used to. I think that other questions in Java that have simple return statements would be fairly easy for you to trace, which is why I really just wanted to focus on this one right here. Now, this is actually the question we went over before with the palindromes, and I just wanted to show this to you so I could give you an idea of what this actually looks like in an IB context. So it says a palindrome is a word that spells the same backwards. We have some examples right here, and we have a description right here. And that logic with checking the first and last letter is not something I came up with my own. That was actually given to you in the question. So that way, you know that you don't need to worry about trying to come up with those more complex recursive solutions. That'll be given to you, and then it's up to you to not even code it, but you just need to describe the recursive method palindrome that returns whether or not a word is a palindrome. So you're basically taking this, and then you are verbalizing. Well, not really verbalizing, but you're basically explaining how that would work in a coding context. And you've got another theoretical question explaining why recursion is a suitable tool when performing this check. And the answer to that one, the theoretical question, is basically what we went over in our tips. The solution repeats the same series of steps over and over again. There's a changing parameter set, and there is a clear base case. So if you just go back to the tips that I gave you for solving recursive problems, those are also simultaneously tips for how to identify recursive problems. And that's pretty much your answer to like when you would use recursion. So some of the ideal use cases of recursion are what we're going to see next, which is traversing tree-like data structures. So specifically, the next section is going to be about binary search trees. And partly because with binary search trees, you're starting with a node, and initially you're not exactly sure how far you're going, but you do have a base case, which is when, you're going to stop iterating through or going through a binary search tree when you hit a node that has no left or right node. So what I want to make clear is that whenever we have a tree-like data structure, which is just binary search trees, also just known as plainly binary trees in HL, is a case in which we would want to use recursion. And we'll go over that in more detail in our next section. Furthermore, another good use case is solving mathematical problems. So we've gone over the Fibonacci sequence in the past. The Tower of Hanoi puzzle is probably something I'm just going to make a video about, because I actually never understood how to solve it using recursion, but I think I kind of want to, and I think you guys should too. And the reason for that is that recursion can be used to break down problems into smaller subproblems, and we can continue to solve those until the final solution is reached, or more specifically, when we hit that base case that indicates a final solution has been reached. So traversing tree-like data structures, which also include file systems, and solving math problems are two ideal use cases for recursion. Okay, so binary search trees. Now, in terms of binary search trees, we're going to be doing three sort of basic tasks. The first is to create and initialize a binary search tree. The second is to use recursion to traverse a binary search tree and print out all of the elements. And then the next is to find the minimum value in a binary search tree. And this is an example of just the kind of task you might have to do on the IB exam in terms of navigating a binary search tree, which is also going to use recursion. I would have liked to give more examples, but this video is already running pretty long, so just in the interest of brevity, we are going to stop right there. Anyways, this is a binary tree we're going to be constructing and working with. I'm going to go ahead and we're actually going to go through an example first, and then I'm going to explain the why in terms of why we use recursion for binary trees and kind of what the logic is here in terms of navigating them. So what we're going to do is I've already written a node class, and this is so we can create node objects. Now this has a left and right attribute, both of which are also node objects. And this isn't really like recursive or anything, because when we initialize a node object, we're just sticking in data. We're not specifying the left and right node. So we're going to have this node object, and then we're going to have attributes for the left and right node on that node object. So basically the leaves for that particular node, as well as the data, which in this case is just going to be an integer. So we're just going to be talking about a tree, a binary search tree of integers. Now what I've also gone ahead and done is I've created the tree root, which has an integer value of 50 and 6 leaves of varying values. Now for the tree root, I basically said the left node is going to be leaf 1, and the right node is going to be leaf 2. So the left node is going to be 25, and the right node is going to be 75. So 75 and 25, right and left. And then I've basically written this code right here. So then I have leaf1.left equals leaf 3. So leaf1.left equals leaf 3, which is 19. And leaf1.right equals leaf 4, which is 27. And then leaf2.right equals leaf 5. So this one right here is going to be 21. And then right down here for leaf leaf3.right, or actually leaf2.right equals leaf5 is going to be this one right here. So leaf2 is 75 and leaf3 is 78. Or sorry, leaf5 right here is 78. And then we also have leaf3.right. This is leaf3. And then leaf3.right is going to be 21, which is just leaf6, which is right here. So that's a really like specific overview of like what our tree looks like and how we build it. This is just a tree of node objects, and they are all connected through these attributes right here. So now that we have this binary search tree of nodes, what we want to do first is we just want to be able to print out what's in the binary search tree. So to do that, we're going to use recursion. And the reason that we use recursion is because we're basically navigating a tree of indeterminate size. We may not know exactly how big it is. And we have an individual set of instructions that we can execute each time. So every time we go to a node, we want to check the right and left leaves. And in this case, we're going to print out our values. But in general, when we're working with binary search trees, that's what we're trying to do. We're checking the right and left leaves. And finally, we're executing operations based on the previous result. So when we're talking about mathematical problems, like for example, Factorial or Fibonacci, we are executing our subsequent operations based on the sum or product that came before. And that's our previous result. In this case, we're executing subsequent operations based on the previously accessed node. So based on what the previous node was, then we're going to decide what to do next. So that being said, let's go ahead and let's write some code and let's see how this works. So the first thing I want to do is print out all the values in this tree right here. And I don't really care what order it is, I just want to print all of them out. So I'm going to say public static void, because we're just going to be using a print statement, output tree. And then I'm going to put the root node, the absolute, like, so the root node of the entire tree right here as the input. And that's generally what the parameter is going to be for almost any methods you're writing on the IB exam. That is related to binary search trees. So the first thing we're going to do is we're going to say if root equals null, then just return and just stop, because why would you bother doing anything at that point? There's no data there to print out. And what we're going to do next is we're going to do output tree root.left and output tree root.right. Now, these functions, noticed, aren't preceded by a return statement. So right here, we're just executing these functions recursively, and they're just going to keep going until they hit a null node. So for example, like for this one right here, if we go back to our node and we'll go to this particular output right here. So we're going to start at 50, or this particular tree right here. We're going to start at 50, right? And then we're going to go left, and then we're going to go, so we're basically going to just call this function right here. And from this instance right here, we're going to go left. And then we're going to go left. And then we can't go left anymore, so we're going to go right. And that's going to carry back up. And then from this node, or well, from this node right here, we're probably going to go right. And then we won't be able to go left. That's going to return null, so we're just going to go right. So in a way, what we're doing is we're executing this function, and we're letting that basically run until we hit something that's null. And then once we've executed this function, we're going to execute this function from that initial root node, and we just keep going until we hit null. And that could be at any point in time, because remember, we're doing this recursively. So when we call root.left, this node is going to become the parameter, and then we're going to do both right and left for them. So through that methodology, we're systematically going to cover all of the right and left leaves throughout the entire tree. And as we do that, we're actually just going to print them out. So we'll do system.out.println. I just want to do this so that we print out the data associated with the node as soon as we get to it. We could put it here. I think in the example, I put it right down here as well, which we can do that as well. But now that we've done that, let's go ahead and let's run it and see whether it works. So we're going to do output tree, and then we are going to put in our tree root. That's our topmost node, and then just run it. And okay, we've pretty much got all the values, 21. So it's interesting to see the order, right? So right here, we're actually not printing the first node until we get to the end. 50, 75, 78, 25, 27, let's see, 19, 21. So I guess the interesting thing is actually we end up going to the very bottom node right here first, and then we're working our way up, which is really similar to how our trace table problem worked in the recursion section before. So we're kind of going all the way to the bottommost point and then just working our way back upwards. So now that we've done that, we're going to do another simple problem involving recursion. That's just going to be to find the minimum value in a binary search tree. Now, I actually found this on an IB exam. And to be honest, a lot of the binary search tree problems I've seen have not been this hardcore in terms of using recursion. But this is a good example of how we might have to use recursion to navigate a binary search tree. So that being said, let's go ahead and let's write that function. We're going to say binary public static int, because we want to find the minimum. Find minimum. Our parameter is going to be again the tree, like the root node, and we're going to say if root.left. So think about like a binary search tree, right? Like our minimum is going to have to be on the left because it's going to be a smaller value, right? It's going to be the smallest value, in fact. So it's going to be somewhere over here. So if that left node is immediately going to be null, then we know that whatever our node is, whatever our root is right here, is going to be the smallest value because everything on the right is going to be larger. So immediately that can be our base case, and we can just say return our root.data. Now, for our recursive step, if that's not the case, then we can do return find minimum root.left. And the reason we can do this is because we know that our minimum is always going to be on our left, right? So let's say we have, this is our root right here, we do root.left and we go right here, okay? And then we do root.left, we're gonna get 19. Root.right, even on 19, was gonna be greater than 19, right? And right here, even if 19 didn't exist, we wouldn't go root.right because that was gonna be greater than this existing node. So if this didn't exist right here, we wouldn't even go here because that would be root.left equals null. We would just stop at our existing node and just return that. So let's go ahead and let's give that a try. We'll do, let's say int minimum equals find minimum. And tree root will be, we do right there. Then we're just going to do system.out.println minimum. And I definitely spelled that wrong. You've seen my spelling mistakes before. All right, cool. Okay, let's give that a try. And we got 19, which looking back at our leaves right here looks correct. Okay, so those are our two main code examples. Let's talk a little bit more about binary search trees now. This is sort of a way to illustrate the logic. But so I want to talk about the pros and cons of binary search trees. So some of the pros are the fact that we can search really fast. So we can search through a binary tree for a value a lot faster than we can through just an array. And this corresponds to the difference between binary searches and linear searches. Next, we have a dynamic structure. So this is a dynamic data structure, so we have easy insertion and deletion of nodes. And furthermore, binary search trees are generally pretty easy to implement and debug. So we create a binary search tree there really quickly. However, there are some caveats to that. So first, because nodes are allocated dynamically and they require pointers, pointers take up memory, and this can lead to heavier memory usage. And furthermore, when we delete a particular node, we need to rebalance the whole tree. And while it can be easy to just create a binary search tree that's already balanced, that rebalancing can be complex and can lead to unforeseen errors. Now, just to get into like kind of why searching a binary tree is faster. Let's say that we wanted to find the number 9, right? And we were just looking through an array. We're just doing a linear search. We'd have to go 1, 2, 3, 4, 5, 6, 7, 8. And we'd have to go through all these elements until we get to 9, right? Versus in a binary search tree, we could say, hey, we want to find 9. So let's go down to 4. Is 9 greater or less than 4? It's greater, so let's go this direction. Is 9 greater or less than 8? Cool, okay, let's go down to this direction. And then we hit 9. So in that way, we can more or less, so really the speed at which we can find something is measured by logarithms. But what we can say is that the speed of finding something in a binary tree is at least faster, because we can already eliminate, because we're immediately at each operation eliminating other possibilities, rather than just kind of brute force just going through every single value until we find what we want. So with a binary tree, we are never going to have to go through, we're almost never going to have to go through every single value, because the structure of binary trees means at any given point in time, we are eliminating at least one other node, or one other set of nodes. So it could be more than one node, right? And that's kind of why a binary tree is faster. Now, some of the use cases or ideal use cases for binary search trees are anything that involves sorting. So binary search trees can be really good for not only sorting elements, but storing them in a certain order. Elements can then be accessed using what we just talked about in this particular case, right? And moreover, in order to sort the elements in a particular, or in order to get elements in a sorted order, we can perform an in-order traversal. I'm not going to go through that. You don't need to know too much about that, but that just speaks to the point of why BSTs or binary search trees are good for sorting. Next, if we want to maintain a data set with only unique elements, binary search trees are useful because they automatically discard any unique elements, any non-unique elements, so any duplicate elements. And finally, a common use case for binary search trees is database indexing. And this kind of applies to search engines as well. But data can be stored in a binary search tree in a database in order to allow for more efficient searching and sorting of the data. Okay, so that wraps up the HL portion of option D. I was going to do a practice exam, but honestly, just making this particular video has been so exhausting that I decided not to. And the reality is that all of these tasks were either directly came, so all the basic tasks I went over, either directly came from the IB exam or were inspired by the IB exam. So having completed and understood all those tasks, you should be in a good position to be able to conquer any any option D HL paper. Now, while at the time of releasing this video, I am also going to be releasing the option D study guide, and that's going to include slides as well. Now, I'm going to be adding some information that I may have accidentally left out in the SL portion, and perhaps in the HL portion. With SL, there was particularly a section on dependency that I wanted to include but didn't end up including. So that information can be found in the study guide and slides. And finally, I haven't created it yet, but I'm planning on creating an Intro to Java course. And this is probably a course, like a video course, that'll be paid for on my in my online store. And this is kind of to give those who are having a lot of trouble with Java sort of a very basic and ground level understanding of how Java works and like the basic syntax, so that from there they'll be able to go ahead and understand the SL and HL portions of the video. Anyways, as exhausting as making this video was, I enjoyed it and I hope you do too. If you found value in this video, please like and subscribe to the channel. Have a nice day and good luck.